Kristen Atchison here, and we're going to be talking about Anova versus t-tests. When you're doing a t-test for two independent samples, you can either use a t-test or an Anova with the F ratio. Either one's the same, and you're going to always come up with the same decision. We're doing the same things, we're just going about them in different ways. Because of that, your F ratio will equal the value of your t value squared. So if you have a two sample Anova, you have two groups in an Anova versus a t-test. If you calculate those out with the same data, you're going to get the same value if you square your t-value. They're going to be equal. It's another good way to practice and check your work as well. And the same is true of the alpha value. The t critical squared is equal to f critical. So if you've got if you're doing if you don't have an F table and all you have is a T table and you're doing a study again with two samples, this only works for two samples, you can square that table value to get your F critical value. So again, the relationship is the same. The reason this works is because of their distributions. And again, we have the difference also of and this is for two-tailed tests, the t-value squared for a two-tailed test, because of how the distributions work. Remember, a t distribution has more of a normal shape to it, and so we can have two tails. That F distribution, the bottom value, doesn't have that. But if you look at the values, we have plus or minus 2.101 for the t-test. If we square that value, we get 4.41 on our F distribution. So again, we still have 5% in the tails versus, and it would work for 1% in the tail as well, and then 95% that's not in that critical region. So again, this works both ways. When we're talking about the assumptions of the independent measures, Anova, and Anova as a whole, especially for the independent measures, the sample has to be independent, just like t-test. These are the same assumptions that you would see in a t-test, because again, they are so similar. They're just approaching them from different angles for two samples. The population for which the samples are selected must be normal. Again, if we have a really distorted population that has a very strange distribution, that's not going to work, because F distributions are based off of normal distributions and probability. Because again, we're saying that there's a 5% chance or a 95% chance. When we're doing those critical values, again, we're working off of probability. So probability has to work off of that normal distribution for this to be valid. And the populations from which the samples are selected must have equal variance. Again, they must have homogeneity of variance, just the way we had in the t-tests. And violating that assumption of homogeneity of variance risks an invalid test results. If they have very different variance between the two samples, then it may look like we have an effect, but really it's just that they were very different samples to begin with. Because remember, an analysis of variance, we're looking at the variance between two groups versus the variance within groups. And we're hoping that whatever our independent variable is, whatever our treatment effect is what's causing the variance between groups. Well, if you have very different groups to begin with, then that variance between groups may not be caused because of our independent variable, but may have to do with this violation of homogeneity of variance. So again, we have to have that in place before we can do an F test, because if we're doing an F test on this, again, we may get this invalid result based on just the difference between these samples to begin with. Again, these assumptions are basically the same as t-tests. Again, they're the same curve, so once again, we have that same relationship. The equal variances, again, the same. Again, just like t-tests, moderate violations are not a problem, except, again, with large variances in that homogeneity of variance. And it's okay if the largest estimated variance is more than 4 to 5 times the estimated variance. and the sample sizes are equal. So again, if we have a balanced design and we have this, these modest violations aren't a big deal and it doesn't invalidate our test. Again, this has a lot to do with probability. This has a lot to do with that it's an analysis of variance. Both of these things are contributing to these kinds of violations. But I hope you see that t-tests and ANOVAs, they have the same kinds of assumptions. And they're using the same kind of techniques. Again, when we started doing these ANOVAs, we started out the same. We started out doing sums of squared, which is the same thing that we would do in a t-test. We're just using that sums of squared differently in a ANOVA as compared to a t-test. And that has to do with the difference of how we use the mean. We're going to be using means in t-tests. We're not using means in our final F ratio. We're only using that estimated variance in our F ratio. So it just is a difference of how we look at it. And so when you're looking at only two groups, either one can be used, and one can be used to check the other, because again, there is that relationship between the two.